In tape number 2, Bob Hoskins shows us 2 methods of putting satellites into orbit, as well as a look at the construction of a typical communications satellite and how it is kept in orbit. We also take a look at uplink and downlink technology.
I just made myself sick showing you what a geosynchronous orbit was, and now we need to look at how the space satellites that are up there now were placed into orbit. They were put up there by being launched from the space shuttle. First, let's look at how the shuttle actually gets launched.
This is shuttle launch control at T-minus 20 minutes, 48 seconds and counting. We're just a few seconds away now from the T-minus 20 minute hold, and we will stop the clock at that point.
Flight NTD on air ground 1. I copy, and they're moving to the west. Okay, and you're still go. Engineering director. Launch director, this is engineering director. I have polled the technical community, and you will have our consensus to proceed with this launch. Good luck and Godspeed. Copy, KSC Safety and Quality Director.
This is the walkway used by the astronauts to enter the orbiter. In case of an emergency, the arm can be placed back into position within about 15 seconds.
Okay, we copy.
Coming up on the 4-minute point in the count, the orbiter flight control surfaces such as elevon, speed brakes, and rudders are now being moved through a pre-programmed pattern. That's all 3 engines now being moved in a pattern to verify their readiness to support the ascent flight control. After going through their paces, they'll be aligned to their start positions. Coming up on the 2-minute point in our countdown, T-minus 2 minutes and counting. The orbiter computers have positioned the vent doors, T-minus 31 seconds. We have a go for auto-sequence start. Discovery's 4 redundant computers have assumed T-minus 23 seconds and counting. The SRB nozzle profile, T-minus 15, 14, 13, 12, 11, 10. We're go for main engine start. 7, 6. We have main engine start. 3, 2, 1, 0, and liftoff. Liftoff. Americans return to space as Discovery clears the tower.
Roger, roll, Discovery. Crew confirms roll program. Houston now controlling. 3 engines at 104%. 3 good APUs, 3 good fuel cells. Standing by to begin throttle down to 65%. Engine throttling down now to maintain a certain speed as the spacecraft passes through max Q.
No matter how many times I see a space shuttle launch on television, I still get excited watching it. Once the space shuttle achieves its low Earth orbit, the cargo bays are opened. And the space shuttle flies in orbit with the cargo bays open, and the satellites, which are stored in the aft portion of the cargo bay, much in this fashion, like I'll just use the yo-yo, and then it is actually spun out of the cargo bay, and it floats out into space until the space shuttle can get enough separation from the satellite that the rockets boosting the satellite will be able to be fired without affecting the space shuttle. I'm going to go to this illustration here that will show us a little bit better how it is performed. Okay, the space shuttle goes into the orbit. It rotates in a position, a relationship like this. And then you can see where, just like I showed you with the yo-yo, the the communication satellite is spun out of the space shuttle. And because of its increased velocity, it starts to track an orbit a little bit different than that of the space shuttle. Right at this point, a payload assist module, it's a motor on the payload assist module, fires, and it starts to move the spacecraft out of the low-level Earth orbit that the space shuttle is in, so that it can start to seek its own geosynchronous orbit. Now, I just used the term payload assist module. That's this portion of the spacecraft right here that is attached to the satellite. And what that is a rocket motor that causes the satellite to be pushed into its higher level orbit over the equator. Because as I was saying, the space shuttle can only obtain a low-level Earth orbit far short of the 25,000 miles out into space that it must attain in order to have geosynchronous orbit. And again, the spacecraft or the satellite is pushed up into the position by the payload assist module. Now, just a second ago, I told you that the satellite is spun out of the space shuttle. Okay, it's done this way for two reasons. One, it spins. The satellite has to spin all the time, because what that does is it keeps the solar cells rotating, and they all take their turn collecting the energy of the sun in order to power the satellite. And also, by spinning it, it's a form of gyroscopic stabilization, so it helps to stabilize the spacecraft also. So it's spun, that preserves the spacecraft, makes all of the solar cells do their job, and it also helps to stabilize the spacecraft. As soon as the spin is affected and is correct, then the payload assist module can fire and push the satellite into its proper Earth orbit.
Since the tragic loss of the Space Shuttle Challenger, NASA has only allowed government and military satellites to be launched via the Space Shuttle. This has created a problem for those commercial companies that wish to launch telecommunication satellites. Now, new companies are being formed that will offer other methods to place satellites in orbit. Let's take a look at one of them.
America's capability to place scientific, commercial, and national defense payloads into orbit has taken a quantum leap forward as a result of the ingenuity and vision of two premier aerospace companies. Orbital Sciences Corporation and Hercules Aerospace Company have joined together to privately develop a revolutionary small satellite launch vehicle called Pegasus. Unlike other space launch systems, Pegasus is launched from an aircraft rather than a ground launch pad, providing new operational flexibility and increased payload performance. 30 years ago, America's X-15 rocket-powered research aircraft first crossed the boundary between air and space. In nearly 200 missions, the highly successful X-15 demonstrated the principle of rocket launch from an aircraft. Pegasus combines this proven concept with the latest in advanced technology in the world's first air-launched space booster. Pegasus introduces unprecedented mission flexibility. Operating from any of a number of suitable airfields, Pegasus is launched over large ocean areas for enhanced safety. Weather constraints are reduced as Pegasus is launched well above the rain and lightning that have hampered ground-launched systems. Pegasus can launch payloads into orbits of any inclination. Due east from the equator, due north or south for polar orbits, even retrograde orbits. High-altitude suborbital missions can be flown to assist in hypervelocity vehicle development. Pegasus also achieves a breakthrough in launch vehicle performance. Using advanced technology and the air launch method, Pegasus can deliver approximately twice the payload weight of a comparable ground-launched booster. Delivering 900-pound payloads to low Earth orbit, Pegasus fills a gap in America's launch vehicle inventory. OSC developed and is now producing the transfer orbit stage, a space transfer vehicle compatible with the Space Shuttle and Titan launch vehicles. Pegasus was conceived in early 1987 by OSC's chief engineer, Dr. Antonio Elias, who heads the Pegasus design team. OSC is using state-of-the-art engineering tools for Pegasus development. Computer-based design and analysis techniques assist in Pegasus system design and mission analysis. Aerodynamic and aerothermal characteristics of the vehicle will be analyzed using computational fluid dynamics methods with the help of NASA's numerical aerodynamic simulator, using Cray supercomputers at NASA Ames Research Center. With its team of support contractors, OSC is developing Pegasus subsystems for aerodynamic flight control, guidance, and airborne and ground support. The all-composite wing and fins are designed and built by Scaled Composites Incorporated. Scaled Composites is headed by Burt Rutan, known for the design of the Voyager aircraft that circled the Earth without refueling. To ensure the reliability of the Pegasus satellite launch system, Hercules is employing production technologies and components from its many successful defense and civil space programs. Hercules rocket motor manufacturing facilities are the most modern and fully automated in the world. The Hercules Bacchus West plant has established a new industry standard for quality and reliability. Case and propellant ingredient preparation, as well as propellant mixing, casting, and curing, use sophisticated robotics and built-in quality control and safety features. Pegasus could revolutionize American space launch procedures. Designed to be assembled horizontally by a small team in aircraft hangar-type facilities, Pegasus provides significant access and handling advantages over traditional ground-launched boosters. After final assembly, testing, and payload integration, Pegasus is mated to a carrier aircraft that delivers it to level flight conditions equivalent to those of a commercial airliner. After release from the aircraft and motor ignition, Pegasus follows a nearly vacuum-optimal lifting ascent, using its wing to fly a unique S-shaped trajectory. Utilizing this lifting ascent technique, Pegasus delivers payloads into final orbit less than 12 minutes after aircraft release. The unique flexibility, performance, and cost advantages of Pegasus will enable a new class of orbital and trans-atmospheric missions.
As I was saying, in this position, the satellite is ejected from the cargo bay, spun by the spin table, and then the PAM motor ignites and pushes the satellite into its orbit. But it doesn't just put it into an orbit where it's supposed to be. What it does is that it takes, let me show you on the board here, it takes the satellite, which has been ejected here, the PAM motor fires and ejects the satellite into an elliptical orbit. And it actually orbits the Earth something like this, where it's in a low-level orbit for part of its flight, and then goes to a point that is almost to its final destination later on in its flight. And then as it gets to a certain point in its flight, the payload assist module fires again and broadens the elliptical orbit, and does this in stages, and just kind of stretches out the corners until in final eventuality, by timing the firings of these motors, it is actually put into the final circular orbit over the equator. And by timing these firings just right, the satellite can then find an eventual positioning over the equator. And then there are small rocket jets on the satellite located at various positions on the satellite that allow you to actually fly the satellite into what we call a box. The box is an invisible square in the sky between 90 and 100 miles on a side, and the satellite is positioned in that box, and when it's in that box, then it's said to be in position. And you have little rocket motors. They're actually what we call inert gas engines, which are fired periodically by the ground controller on the Earth that keeps the satellite in position. A satellite, once it's put into orbit, has to be constantly tracked and constantly flown. And it's flown by a ground control team who, by analyzing computer data, can tell what action needs to be taken in order to keep that satellite in its box or predefined and predetermined position. Because if the satellite leaves that box, then we lose the satellite. A satellite, communication satellite, is more than just a satellite. It's actually a collection of systems. Of course, what makes the electronics communication systems on the satellite work, or what supplies it the power to work, is the solar array. Now, the solar array is a set of panels that usually on most of the current satellites go all the way around the bird. I'm going to call the satellite a bird. Because that's what they call it in the space business, is the bird. Anyhow, you will see a whole collection of solar cells all the way around the satellite or the bird. And as it is in orbit, it rotates. And it rotates for two reasons. One, it allows you to use the whole solar array all the way around the satellite in which to collect the power, from which to collect the power. But it also allows for uniform cooling of all the components and uniform warming of all of the components in the satellite. Since you're in the vacuum of space, if you have the satellite up there without it spinning, one side of the satellite would eventually cook and the other side would eventually freeze. So it rotates, and thereby allowing exposure to all of the solar cells so that you can collect power all the way through. Also, while you're orbiting in space, you pick up dust particles and other things collide with the satellite, and if you didn't spin, certain cells on the solar array would become damaged and no longer effectively collect the power for you to use in the satellite. So at any rate, by spinning, you are able to use all of the cells, and that way when you lose 10 or 15% of your cells due to damage, well then it will continue functioning. Also, you have an antenna system. You have an antenna system that is used to collect the signal, and then an antenna system that allows you to rebroadcast the signal back to Earth. We do this by the use of a transponder. A transponder is a device that allows you to receive a signal at one frequency or channel and transmit at another frequency or channel. The reason why we do that is because if we received on one channel and transmitted back to Earth on that same channel, the signal coming from the satellite would interfere with the signal coming up from Earth and vice versa. So what we do is we receive the signal from Earth with one set of channels. It's collected by the receiving antenna, and then we retransmit on a different band of frequencies, and that would be that antenna. Now, this satellite is spinning, so we have to have a stabilization system, plus we have to have a system that allows us to rotate the antennas, because what happens is that the whole body of the satellite is spinning. Well, you have to have a spinning mechanism on the antenna that spin it in the opposite direction at the same speed that it's rotating, because that antenna has to be aimed at the exact same spot on Earth. So you have the satellite spinning this way, then you have the antenna spinning this way, so that the signal can be focused on one point on Earth. So you have an antenna system, a solar or battery or a power system, and then of course you have a thruster system. That's the system of rockets on the satellite that allow it to be flown and kept in its position up in space. And then of course the transponder system, that's your set of receivers and transmitters that allow you to actually perform the function for which the satellite is actually put into orbit. That is, receive communications from Earth, process them, and then retransmit them back to Earth again. In a satellite communication system, there are two very vital components, the uplink and the downlink. Here we show an illustration of an uplink. It's a large dish at a transmitter site on Earth. What it does is it feeds a signal up to the satellite. It is picked up by the satellite antenna system. It is picked up on a frequency or a channel, different than the channel that it's going to go back to Earth on. Then at another location on Earth, and I'm going to draw the downlink on Earth as a smaller illustration because downlinks are typically much smaller in size than uplinks. I'm going to try to get it halfway aimed. We'll make a dish like this, and the downlink dish is smaller than the uplink dish, and it's located at a site some distance, sometimes a long distance, sometimes a very close distance from the uplink. The signal is broadcast up to the satellite. It's processed in the satellite, retransmitted on a separate channel to the downlink. We use the term uplink for the transmitting site on Earth that is going to supply the signal to the satellite, and then the downlink is the system which receives. Everything we've been doing up to now has been leading up to the introduction of this satellite Earth station. This is a complete satellite receiving station. It includes the reflector, the pickup, and all the other equipment, plus the receiving equipment, which is behind the system here. This is capable of picking up complete satellite broadcast from a satellite orbiting over the equator of the Earth. Are there any questions?
Yes, Mr. Hoskins. I was wondering why this one is so much smaller than the one in my neighbor's yard.
I take it your neighbor's is quite a bit larger. Okay, probably your neighbor's system is a C-band satellite system. We have two systems of satellite broadcasting, or two different types of equipment. One is the KU band, which this is. And then we have the C-band, which has been in use over a much longer period of time. Now, the C-band satellite system operates at half the frequency, or half as high a frequency as the KU band. Now, the C-band satellite system broadcasts on the same microwave channels as what all the telephone companies use on repeaters all over the United States. And because of that, the C-band systems have to broadcast with a very low power or very low signal strength in order to not interfere with all of the microwave systems that are already in place on our continent already. Now, because the signal is so weak, you have to have a very large dish or an antenna or a reflector to gather the signal to be able to concentrate it to the antenna and have a usable signal. So it takes a large dish. The KU band, because it's being used in frequencies that we don't use commercially, around the world, because it's on much higher frequency, they can broadcast at a much higher power. Well, because it's coming from the satellite at a much higher signal strength, you don't need to have as large a dish, and you don't need to collect as much signal to be able to have a usable picture. And that's why the KU system is a much smaller antenna or a much smaller reflector than the C-band. Do I have another question?
What are those things in the front of the satellite?
Okay, this is the actual electronics. A lot of people think that this is the antenna. This is not. This is a reflector. And what it does is it gathers the signal from the sky and goes ahead and bounces it down, and it's picked up by these two devices. This is the feed horn. It directs the signal to be picked up by an antenna that's in here. And the antenna is only about 1/4 of an inch. And it takes the signal from the antenna, processes it in this box, which is called a low noise block down converter. It processes it, it lowers it in frequency, or it lowers the channel to a point that it can be transmitted in this kind of a cable. If we were to try to transmit or carry this signal at the frequency that it comes in on over this cable, it wouldn't get very far. We'd lose it all. So this device lowers the signal frequency, or the rate at which it's operating, down to a frequency that can be transmitted down to this cable to the receiver. And it makes it to where we can actually also go over a long cable, so that this dish here can actually be placed outside, and we can run over 100 feet of wire to the classroom, so that the receiver can be inside the classroom or the home or whatever while it's being used. So this is the pickup, and this is the low noise block down converter. Another question?
Yeah, how much can you move the dish and still get the picture?
Oh, if I'm watching a television picture, and if I move this dish this much, we've lost the picture. That satellite is positioned over the Clark belt, and the antennas are so directional that if I move 1 inch in any direction, I've completely lost the signal. That's the reason why you have to be careful when you set up and aim the system. If I raise and lower it that much, we've lost the signal. Any other questions?
How does the signal get from the air to the receiver?
Okay, I almost answered that just a little bit ago, but I didn't quite finish. What happens is that the signal comes in, it hits this spherical reflector, and all of this area gathers signal and reflects it back to one little point. And you notice how this kind of tapers down? Microwaves are very, very directional, and they can be guided. Okay, just like you can take and set up like a cattle chute, and you're driving cattle into a thing where they have to go up into the truck or whatever. Well, they come from a lot of different directions, and they are guided by this fence until they go into like a funnel, and then they go into one specific place. Well, what happens is that you've got signals over a large area that are picked up, and they hit this way, and because of the curve of the dish, they will bounce. Any signal that hits right here will bounce right to here. If it hits here, it will bounce right into here. If it bounces here, it will bounce right into there. And it focuses it and magnifies it. Do you remember playing with a magnifying glass as a child, and you sit there and you focus it in on a piece of paper, and it brings the sunlight until it comes to a very, very, very tiny spot, and then that spot gets so hot that it'll start burning paper? Yeah, I could tell you were a firebug. Anyhow, this does the same thing with microwave signals, and puts the signal right down in here, so it can be amplified, processed, and run into the system so that you can watch television pictures. Do I have any other questions?
Yeah, what types of programs can you pick up?
Okay, with KU systems, you can pick up just about any kind of programming that you can in the C-band, except basically now they're using it because it's so you can have a much smaller dish with it. They use the KU band for news gathering, uplinking. In other words, they take a truck out in the field and they can send the signal back to the local television station, and they use it a lot for teleconferences. At schools now, they're using it a lot in schools for teleconferencing, because they can have a meeting like in Sacramento or Austin, Texas, or someplace like that, and they need to get information to a lot of teachers in a lot of areas. So you can take a system like this where you store it in your classroom, and you take it right out, you set it up in a few minutes, and then you can receive a teleconference that you can have a bunch of teachers watching at once. They use it a lot in business, too, for business teleconferences. Even HBO has some channels, but because of economics and they're owning different transponders on C-bands, most of your entertainment stuff is going on the C-band systems.